Hi everybody. In these slides we're going to take a look at three new methods which apply to binary search trees, and we previously explored both a find and an insert method along with a display method in some cases. And in these slides we're primarily looking at how we can perform deletions. And there are several distinct methods that we'll discuss whose overall purpose is to remove a given key if it's found in a particular binary search tree. So we have the need really for methods that perform insertion and deletion in BSTs, and both insertion and deletion will modify the state of the tree. Insertion will always modify the state of the tree, and deletion will only modify the state of the tree if the requested key occurs in the binary search tree. And so insertion adds a given key to the right place in the tree. After an insertion, there is one more node than there was prior to insertion. Delete poses several difficulties which insert does not. And after a deletion, if the provided key is found in the tree, it is removed and there is one less node in the tree. So you can think of insertion always modifying the state of the tree, and deletion only modifying the state of the tree if the given key is found in the tree. So here is our tree insert method, and you can see this method has two parameters, a tree and also the address of a node that we would like to delete. And of course, when you go about implementing a binary search tree and you're implementing this particular method, ideally what you have to do is construct a node to represent the key that you'd like to insert. So if you'll remember, in our node class, the key is an attribute of the node. And we also have a parent reference, a left reference, and a right reference. So when we want to insert a given key into the tree, we actually have to kind of set the parameter up. So T is pretty straightforward. That's just the address of the root node of the tree. And Z, of course, is a node that has as the value of its key attribute the key that we would like to insert. And this method is really fairly perceptible. We initialize Y to null, and we're using Y as a node reference. We're also using X as a node reference, which we initialize to the root. And then we basically, using a while loop, we search for the place, or I guess really the address in the tree of where the given key should be inserted in the tree. And of course, we want to preserve the rule which applies to binary search trees, and that's the left subtree always contains keys less than the key in the root, and the right subtree always contains keys that are greater than the key in the root. And that's something we have to keep in mind when building tree insert, because it's that relationship between children and their parents that makes the data structure possible. And as long as we're always making that assumption in the methods that we implement, we'll be able to preserve that as an invariant, and that's something that applies to all binary search trees. And after we're done locating, we end up with this reference y, which is close to where the given key should be inserted in the tree. And we're setting the parent of z equal to y. And if it's the case that y is null at this point, we know the tree was empty, and we can just create a new root. Otherwise, we've found the spot to perform the insertion, or the parent of the spot where we should perform the insertion, and we simply compare the key we're inserting to the key in this node y. And if the key we're inserting is less than the key in y, then we know we need to insert to the left of y. Otherwise, we insert to the right of y. And this takes care of inserting a node in a binary search tree. And so here, take some time to explore the reading. This figure is actually reproduced directly from CLRNS, and it's one of the figures in the reading on binary search trees. And this slide demonstrates how we would perform the insertion of 13 into this binary search tree, which you see depicted here. And you can see we start comparing 13 to 12. 13 is greater than 12, so we know that when we insert 13, it'll be over here in the right subtree. Then we go to 18, and of course 13 is less than 18. We go to the left, and at this point, the left node of 15 is actually null. So we end up with this reference y to this node containing 15. We compare 13 to 15. Since it's less than 15, we know it should go in the left subtree. And the left child of the 15 node is null. So we simply create a new node as the left child of 15. And with a little bit of effort, you should be able to go through the pseudocode on the previous slide for tree insert, and sort of just mentally be able to see why the 13 ends up where it does, and how exactly the algorithm performing the insertion relies upon a loop initially to locate the parent of the node which is being inserted. And here's a method that we sort of meet along the way. This one's called transplant. We have a tree as a parameter. We have u as a parameter. We have v as a parameter. U is simply the root of a particular subtree, which we would like to replace with the root of v, which is also the root of a subtree. And this method, the transplant method, basically just updates the state of the tree so that the subtree occurring at v ends up where the subtree occurring at u initially occurs in the tree. So we have, three parameters: t, which is our tree; u, which is the address of the node, that's the root of a particular subtree; and also v, which is the root of yet another subtree. And all we're doing is checking initially if u is the root node. If u is the root node, we know its parent is going to be equal to null, in which case we just set the root equal to v. And that is then followed up by this test to see if V is not equal to null. And provided V is not equal to null, we set VP equal to UP. And that essentially links V to U, or at least to the parent of U. So we're basically kind of like initially just checking to see if the parent of U is null. If it is, we know it's a root. We're setting up a new root. And then we simply test to see if V is not equal to null. If V is not equal to null, we set the parent of V equal to the parent of U. And then we also have in this if, else block, we have our else if, in which we test to see if U is the left child of its parent. If it is, we set U, P left equal to V. Then the else is we're setting the right child of the parent equal to V. And then again, regardless of which of these conditional statements get executed, either the if, the else if, or the else, we're always checking to see if V is not equal to null, regardless of which these conditional statements is actually triggered. And it's only going to be one of the conditional statements that's triggered. And that is something to keep in mind, and that makes an algorithm more efficient when you're able to determine the distinct paths of execution, and then you could use an if, else if with as many else as ifs as you need, and then also an else. And then we're also checking again, regardless of which these branches occur, we're checking to see if V is not equal to null. And if V is not equal to null, we're setting the parent of V equal to the parent of U. And then this is probably the most sophisticated method we'll look at. This is the delete method. And you can see quite clearly that tree delete, which has two parameters, a tree and also Z, which is a node representing the key we'd like to delete. We have calls to our transplant method, which we just explored. And there's also a call to tree minimum, which was previously discussed. And as you know, the minimum of a given tree is the leftmost node. And that's an algorithm that can be implemented either using a loop or using recursion. And we've actually explored both in the reading and also in prior lectures. So in delete, we basically have an if, else. And again, it's only going to be one of these that triggers in a given call. And you can see the else has actually got quite a lot going on with it. But initially, when we delete, we check to see if the left child of Z is equal to null. If that's the case, then we simply replace Z with the root of its right subtree. And then if Z right is equal to null, we're simply replacing Z with its left subtree. And then if neither Z left is equal to null nor Z right is equal to null, then we know we have both a left and a right child, in which case we get the minimum from the right subtree of Z, and we set that reference to this variable y, which is essentially the address of the minimum, the key, the node containing the minimum key in the right subtree of z. And then if y is not immediately adjacent to z, that is, if z is not y's immediate parent, then we call transplant, and we're transplanting y with the maximum key in its right subtree. And then once we've made this call to transplant inside this if, we're setting the right child of y equal to the right child of z. Z again is the node containing the key we'd like to delete. Then we're setting the right child. I'm sorry, this is actually the looks like the parent y.right.p is, we're setting that equal to y, and then we're calling transplant regardless of whether or not this test expression attached to the if evaluates to true. So regardless of the result here in this if, we're always transplanting z by y, and then we're setting y's left child equal to z's left child, and we're setting y left parent equal to y. And this effectively takes care of performing the deletion. And actually, as you can see, the if up here and the else are pretty straightforward. These are kind of the simple situations we might encounter in which z has no left subtree or z has no right subtree. So we don't get into too much difficulty there. It's just the case in which z has both a left child and a right child that we end up having to do a bit more work. And I'm confident that if you look through these slides in context of the reading, there's an example actually that's given in the book which describes this tree delete method pretty well. And that's what we see here on the next three slides. In A, you can see the left child of z is null, in which case we can just promote the right child and it becomes the root. The other simple case, which we explored, is when the right subtree is null. And this again is pretty straightforward to remove z. All we have to do is promote L, and L becomes the root of the binary search tree. And then in the next couple slides, we're looking at deleting z when it has both a left child and a right child. And in this slide, this is actually a pretty simple case in which z has a left child and z also has a right child. If we're deleting z and the leftmost node in the right subtree is right here where y is positioned, we can simply promote y to z, and that takes care of the deletion. And here you can see the difference here in part D of the tree delete method demonstration. You can see that we have this node Y down here, which is effectively the successor to Z, I'm sorry. And Z is the node we're deleting. So we can kind of separate Z and its left subtree off like this, and we can create a new tree with Y as its root. Y retains its right child, and you can see that X has been promoted to where Y initially was. And then we can just join this tree here with this tree here, and we end up with Y at the root. You can see this is the node that we promoted, and Z is no longer in the tree. And of course, that's the goal of the delete method, is to delete the node containing the key which we'd like to remove.